All right, welcome back. In the upcoming sections here, 4.6 and 4.7, we're actually going to talk about what are called indeterminate limits. And you've actually encountered some of these in the past before. You've actually encountered some of these before, and there were certain ways of dealing with them. What we're going to look at is a new way that we can use, known as L'Hopital's rule, or sometimes thought of, when you have a limit that's kind of broken, what do we do? With stuff that's broken, we take it to the hospital, or at least people we do. And that's what we're going to kind of think about here, and be looking at this way of computing limits that are indeterminate. What are indeterminate limits? Well, you've seen some before. For example, one of the big ones we looked at early on in Calculus 1 is this limit as x goes to 0 of sine x over x. Right? That was a limit that involved 0 over 0. Right? We can't divide that, but yet that limit is equal to 1. That limit was equal to 1. Later on in Calculus 1, we talked about limits as x approaches infinity. And we looked at things like this. Right? And this basically works out as x goes to infinity, the numerator goes to infinity. As x goes to infinity, the denominator goes to infinity. So this actually ends up being a limit involving infinity divided by infinity. But not all infinities are created equal. This infinity divided by infinity actually works out to be 3/4 in terms of a limit. Another one that you saw, this one we did not at the time have a way to work out. We had to just estimate it numerically. This is also a 0 over 0 limit. So we asked the question, what is that? Well, we actually approximated it numerically to get an answer. And then another one that we currently cannot talk about. Limit as n goes to infinity of 1 plus 1 over n to the n. This is actually a 1 to the infinity. Now you know that 1 to any other power is 1, but 1 to the infinity is the thing we can't talk about. This one, like I said, you might have looked at something like this numerically and come up with an answer. We're going to come back later and be able to approach these two questions. But these are all examples of what are called indeterminate limits. There are 7 different indeterminate limits that we're going to talk about. These are numerical calculations that you can't actually compute, yet the limit could still turn out to be some actual numerical value. So, first one is 0 over 0. Second one is infinity divided by infinity. Those are the two that we've kind of seen and worked with some before. Then we have infinity times 0. This was something that kind of came up with, this is something that came up with when you were dealing with definite integrals. We were doing Riemann sums. Basically, essentially, we're subdividing everything to where it got down to 0. We had an infinite amount of intervals. Kind of, in a sense, doing infinity times 0. In a sense there. Not exactly. Fourth one is infinity minus infinity. And then the final 3 all relate to some kind of exponent. And that is 1 to the infinity, 0 to the 0, and infinity to the 0. So these are 7 indeterminate forms that our limits can take on, and we're going to be looking at how we can compute them. And so our first focus is on the first two, which have a thing called L'Hopital's rule, which applies directly to them. The other ones require, this one requires us to use some techniques to transform it into one of the other two. Infinity minus infinity can sometimes be the hardest ones to do. We try to use some different techniques to somehow transform it into one of the original two. And these last three will all require us to use a logarithm, specifically the natural log, to transform it into one of these two. Okay, we're actually usually transform it into an infinity times 0, which we can then transform into one of these two. Okay, so that's the idea here. Let me first just tell you what L'Hopital's rule is, and then in the upcoming videos we'll look at how we can actually use L'Hopital's rule. Okay. So what L'Hopital's rule says the following. So L'Hopital again, it deals with limits that involve either 0 divided by 0 or infinity divided by infinity. Okay. So the rule I'm going to give you here is for 0 over 0 limits. It says, suppose f and g are differentiable so they have derivatives. Differentiable on some interval I containing our point A. And furthermore, we assume that g prime of x is not 0 on the interval as long as x is not equal to a. It's okay for it to be 0 at a. It's okay for it to be 0 at a, but it can't be like completely 0. Okay. As long as we can squeeze I in. Now it's okay if it's 0 other places, but as long as there's at least some neighborhood about the point A where the thing is not 0 anywhere else. Okay. Then we say the following. If, now this is very important, if this condition is not met, then the conclusion doesn't work. And that's actually one of the common mistakes people will make with L'Hopital's rule, is they'll just try to do it anytime. This first thing has to be true for the conclusion to be true. If the limit as x approaches a of f of x is equal to 0 is equal to the limit as x approaches a of g of x. Those two things are true. Then the limit as x approaches a of f of x over g of x, turns out that limit is equal to the limit as x approaches a of f prime of x over g prime of x. So L'Hopital's rule allows me to actually, when I'm dealing with a 0 over 0 limit, Okay, when I'm dealing with a 0 over 0 limit, then what I can do is I can actually look at the limit where I take the derivative of the top and the derivative of the bottom. The hope being that in doing that, I'll transform it into something that I can evaluate the limit of. That's kind of the idea, the hope there behind L'Hopital's rule, is that this new thing will be something I can actually do the limit of. Or maybe I repeat the process another time and do L'Hopital another time and keep doing it until one of these things reduces down to something I can easily do the limit of. That's kind of the hope and the idea behind L'Hopital's rule, and we're going to see it come up here in some examples.